All right, good morning, everybody. Today I'm going to be going over 2014 AP Calculus BC Free Response, and I'm only going to be doing questions 1 and 2. I'll do 3 and 4 tomorrow, and 5 and 6 on Wednesday. And I realize that number 2 on here is a part of the unit that they're not testing on, but it's still good review, still practicing good stuff. So I'm just going to go through with it. Okay. All right. So remember the first two questions here are calculator active. So there's going to be some stuff I say that I typed into the calculator, and if it's calc active, remember that the biggest thing is that you set it up correctly, and then if you can do it in the calculator, just do it in the calculator, because that's always how they have their answer keys, and that's how I plan to do it as well. Okay. All right. So let's do part A for number 1. It says that grass clippings are placed in a bin where they decompose. For 0 to 30 as our time, the amount of grass clippings remaining in the bin is modeled by A of t, A for amount, I guess. It looks like an exponential decay problem. All right, you can tell it's exponential decay because of our rate right there, our decay factor. And it says where A of t is measured in pounds and t is measured in days. Okay, so it looks like we're talking about pounds to or days to pounds. Okay. All right, A, find the average rate of change of A of t over the interval 0 to 30 and indicate units of measurement. All right, rate of change. So that's just your slope, your average slope from the endpoints that it gives you. That's the average rate of change. We've seen that wording a lot. Average, it's not average value, but rate of change means we take the slope. So simply, we're just going to do A of 30 minus A of 0. Oops. Over 30 minus 0. And I typed this in the calculator. So I actually plugged, so this calculator active, I actually plugged this function in for y1 into my calculator. So then on my calculator, all I typed in was y1 of 30 minus y1 of 0 over 30 minus 0. I typed it in just like that and didn't worry about it from there, and I got negative 0.97. Makes sense that it's negative because it's exponential decay. So the rate means it's decreasing. The pounds are decreasing over the time. And the units of measurement here are going to be pounds per day. Okay, so it's negative 1.97 pounds per day is the average rate of change between 0 and 30. Okay, all right. Ah, all right. Let's move on to B. So B says find the value of A prime of 15 and using correct units interpret the meaning of the value in the context of the problem. All right. A prime of 15. That just means we need to find the derivative and know the value at time equals 15. And remember A of t is equal to this. Again, this is calc active. You could try to take that by hand, and I don't think it's the worst thing in the world to do. It looks like it's like an a to the t type of function, so you might have natural log involved in that derivative. But if I have a calculator, if I want to find a prime of 15, I'm simply going to plug that into the calculator. So what I typed in is remember, you can go to the math menu and go down to where you see the derivative operation. It'll come up with like d over d, I did x, okay? I plugged in y1, or I mean simply just a of x into the equation, okay? And I'm evaluating this at x equals 15. So that is exactly what I typed in the calculator. Instead of a of x, though, I had y1. That's all I typed in, and that'll do the derivative for you. It's calc active. It doesn't care that you can take the derivative. It just knows that you can find the value. I think it's mostly concerned with interpreting the meaning. So when I type this in the calculator, I got negative 0.164. And well, I guess pounds per day if you want to give some units of measurement there. But if I interpret that, okay, my interpretation, I want to have at least the word rate somewhere in there. So I'd probably say something along the lines of like um, the rate at which um, the grass is, and I would even say decreasing, because it is negative, it is exponential decay. So the rate at which the grass is decreasing, and remember the derivative is instantaneous rate of change, so you want to say on day 15, so on time 15, is 0.164 pounds per day. And I didn't make it negative because I already said it was decreasing right here. You can make it negative if you want, but I think that's kind of counteracting what you're saying. So the rate at which the grass is decreasing on day 15 is 0.164 pounds per day. Okay. All right, cool. So that's A and that's B. Let's move on to C. So C says, find the time t for which the amount of grass clippings in the bin is equal to, okay, so let's hold on. So find the time t for which the amount of grass clippings in the bin, which is modeled by A of t. Remember, that tells me the amount. So I want to know when this value, okay, is equal to the average amount of grass over the interval 0 to 30. So I'm trying to figure out at what time, okay, is the amount in my bin equivalent to the average amount in my bin. Okay. Well, in order to find that time, I need to first know what the average amount of grass is over 0 to 60, over 0 to 30. And we know how to find the average value. Okay, average value is equal to 1 over b minus a times the integral a to b of whatever my function is. In this case, it's a of t dt. Okay. So literally in my calculator, all I typed in was 1 over 30 minus 0 times the integral 0 to 30. And remember, I had a of t stored in my calculator. I stored it in as y1, so I literally just said y1 and then dx. I typed it in just like that. And when I did that, I got 2.7526351108. I just wrote out the whole thing. Okay. So this is my average amount of grass between the 0 to 30 days. That's my average amount of value in there. Now I'm trying to figure out when exactly my amount of grass is equal to that. So all I did, again in my calculator, is I took my A of t equation. I took 6.687 times 0.0931 to the t, and I set it equal to 2.7526351108. This was in y1. I typed this into y2. I found the intersection in the calculator, and the intersection I got was at time equals 12.415. So at time equals 12.415, the amount in the bin is equivalent to the average amount. Okay, so it's not too terrible. All right. If we're comparing this to the types that we were talking about last week, this would be the type we're talking about, like a rate of change, right? I mean, just a simple, basic, like you can even, I mean, just all the different stuff that can go with a rate of change, pretty much. Okay. All right. And lastly, let's do D. So D says, for time greater than 30, all right, so remember the A of t models it between 0 and 30, but it says any time greater than 30, L of t is now the equation, all right, that we're going to use. It's the linear approximation to A at time equals 30. So we're saying that that's going to be a better model for the amount of grass clippings remaining in the bin after 30 days. So we're going to use L of t once we find it to predict the time at which there would be 0.5 pounds of grass clippings remaining in the bin, and we're going to show the work that leads to your answer. Okay. Linear approximation is just a fancy way of saying tangent line. That's all it is. All I need to do is find the tangent line at t equals 30, and I have my linear approximation. So remember, if I want to find L of t, I'm going to need a point, and I'm going to need a m value. Okay. Now my point is at time 30, so that's 30 comma whatever a of 30 is. Okay. Which again, I typed that in my calculator into my function, and I got that this was at the point 30 comma, what did I get? I got 0.7829278699, and I don't feel comfortable rounding until the very end, so I've just left it like that. And for my slope, I did a prime of 30, again in a calculator, just like I did in part B, and I got negative 0.0559762123. Okay. So I got all the values I need to make a tangent line. Tangent line is equal to y minus y, or y minus 0.7829278699 is equal to my slope, so negative 0.0559762123 times x minus x, or x minus 30. So there's the tangent line at t equals 30. And if I really want to label it as L of t, I'm just going to get y by itself. Okay, so L of t is equal to negative 0.0559762123 times x minus 30, and then plus 0.7829278699. Okay, so there's my L of t equation. That's the best model to do after time is greater than 30 according to this question. Okay, so then it says, all right, we'll predict what time. So time in this case is x here, and I should probably label that t. Sorry. So what time t is this going to be equivalent to 0.5? And again, I typed this into my calculator, I typed 0.5 into my y2, I set them equal to each other, I graphed it in the calculator, and I just found that intersection, and I found the intersection to be time equals 35.054. Okay, there you have it. That ends number 1 for us. Okay, cool. Here is the way it was graded, so we can kind of look over that real quick. Part A was answer with units, which is what we did. We said negative 1.97 and then pounds per day. So that's how you get full credit. Letter B, A prime of 15. The fact that we found that, again, look, they showed no work because they did it in the calculator. It wasn't required to show work for that one. And that we interpreted it. So the amount of grass clippings in the bin is decreasing at a rate, that's the part they really want to see, of that amount pounds per day. And they want you to specify that it's at time equals 15. In part C, they wanted us to find the average value, which we did. And then they didn't really show any work here, but we needed to set that equal to the amount at A at t and find the answer, which we did. We found it to be time equals 12.415. Part D, you get 2 points for the L of t expression, which is what we came up with. They didn't write it out the full decimal like we did. They kind of left it in terms of A of 30, A prime of 30, but that's fine. They set L of t equal to 0.5 like we did and found the intersection in the calculator, and that's how you get full credit. So I think this is a very doable question. I'm really praying and hoping that this is the type of question y'all are going to come across dealing with derivatives. And I mean, because it does derivative, it does integral, it does interpretation, average rate of change. I mean, it's tangent line. So I mean, a lot of stuff y'all know how to do. So I'm hoping that this will be a good problem they ask. So we'll see. All right. So that does it for number 1 on 2014. Let's move on to number 2, 2014. Which is right here. All right. Now, like I said, number 2, I'm still going to go over it because my goal is to do 2014 all the way through 2019, all the questions. And I realize that number 2 has been part of the unit that was taken off, but it's still, good thinking and good review, especially if you move on to Calc 3. So I think it's a good idea to still review it. All right, so number 2 is talking about the area under a curve. You can see in the picture, and it's dealing with polar area. Okay, so I know that wasn't our most favorite thing to do, but I really like this problem. I think it's a pretty doable one, and we've practiced this stuff a lot. Okay, so part A. Well, okay, first of all, the graph of the polar curves r equals 3, which is this circle right here. Okay, and r equals 3 minus 2, or 2 sine 2 theta is this crazy looking function right here. Okay. are shown in the figures above, and we're only looking between 0, the radius 0, all the way down to the radius of pi. Okay, so it does a semicircle. It says, let R be the shaded region that is inside the graphs of R equals 3 and inside the graphs of R equals 3 minus 2 sine of 2 theta, which is already shaded up here for you. Okay. Find the area of R. All right, I'm finding the area of R. Remember, area with polar functions is a sweeping motion. So we start off at 0, and the radius is sweeping across. Okay, it's adding up all those infinite radiuses. Now, as I go all the way across, notice how between 0 and all the way up here to pi over 2, that it's sweeping across one function. And then past pi over 2, it's going to be, the radius is going to be sweeping along that second function. So we should have two separate integrals here. Okay. So first of all, remember that the equation for area for polar is 1/2 integral a to b of r squared d theta. Okay, that's just the area formula. So if I want to figure out this area, the first integral I'm going to have is that one that's going from 0 all the way up to pi over 2, and that's with the function 3 minus 2 sine of 2 theta. Okay. So what that looks like is it's going to be, so area equals 1/2 integral, we start from 0 to pi over 2. My radius is from this function right here, so we're going to put 3 minus 2 sine of 2 theta. I'm going to square it, d theta. Okay, so that's going to tell me this right half right here. And then we're going to add it to the area of this left half here, which if I want to create it as an integral is going to look like this. It's going to be 1/2 integral. Now we're going from pi over 2 all the way down to pi. And the radius is just 3 in this case, so it's going to be 3 squared d theta. Okay. Now, how the answer key does it is they actually set up the same exact integral we did right here for the right half. That's the only way to do it. But for the left half here, instead of saying the integral version, they noticed it was a quarter circle. So they just simply said that's going to be 1/4 pi r squared, or pi 3 squared, which gives you the same thing. And if you can recognize a semicircle, you can do that too. I think most answer keys notice it that way, but you won't get it wrong for setting up the integral as well. Okay. But again, this is CalcActive, and you don't have to be in polar mode to type these integrals in. You can just type them into your regular integral on your calculator. That's what I did, and I got 9.708. All right, so there you go. That was A. Let's move on to B. B says, for the curve r equals 3 minus 2 sine 2 theta, okay, so we're just looking at that funky looking one. It says find the value of dx over d theta at theta equals pi over 6. So in order to do this problem, we need to have x somewhere in here. Okay, we need to have x somewhere in here so I can take the derivative with respect to theta. Well, we've done that before. We know what an x equation could be that relates our functions together. It's an identity we have. So it's actually when we have x equals r, if you remember, cosine theta. Okay, so that's our relationship. And if I want to relate this to my r function, I'm just going to plug that in for r. So I know that x equals 3 minus 2 sine of 2 theta times cosine of theta. So that's what my x, that's how I relate x and theta in this case. And then now simply all I have to do is take the derivative and plug in pi over 6. So d x over d theta is equal to the derivative of this equation with respect to theta. So 3 minus 2, put another parenthesis, 3 minus 2 sine 2 theta, and then times cosine of theta. Okay. And we're evaluating that at theta equals pi over 6. And again, this is CalcActive. So I type that into my calculator under my derivative menu. Again, you don't have to be in polar. You can treat this as an x, this as an x, this as an x. You can treat those as x's and it'll give you the same exact thing. But that's all I did was do the derivative of this function in the calculator, and I plugged in pi over 6 for x. So whenever you type that in, you get negative 2.366. And again, they're not counting on the fact that you can take that derivative by hand. You're able to do that derivative by hand, but I don't recommend it. Okay, I recommend doing any calc active problems, derivative or integral, in the calculator. Okay. All right, so that is the rate at which the x value is changing at pi over 6, in case they ask you to interpret it. Okay. All right, cool. Let's go on to C. All right, then C. C says the wording here is confusing, but it's not that bad. It says the distance between the two curves. So that's r equals 3 and r equals 3 minus 2 sine 2 theta. And we're looking at that between 0 and pi over 2. So the distance between the two curves is obviously changing. All right. I mean, here is one curve between 0 and pi over 2, and here's the other curve. So the distance between them is changing. All right. You can see that the gap's getting bigger and then smaller, and it wants us to find the rate at which that distance between the two curves is changing with respect to theta whenever we're at pi over 3, which is somewhere right here. Okay. All right, well, if I want to find the rate at which my distance is increasing or decreasing, the rate at which it's changing, I need to have a function for this distance, and then I'm just going to take the derivative because that's what rate is. Well, what function can model the difference between these two functions? Well, how about I just take this outer function and subtract this inner function? Wouldn't that mean, if in respect to theta, like if I wanted to know, like, say, the distance from this point to this point, okay? Well, I'm just going to take this outer radius, subtract the smaller radius, right? That's how you figure out that distance. So distance is simply going to be the outer function 3 subtract the inner function 3 minus 2 sine of 2 theta. And that's going to tell me the distance between the two functions, the length of the radius, okay, with respect to theta. And if you simplify that, that just goes down to 2, the 3's cancel, it becomes 2 sine of 2 theta. Okay. So simply put, if I want to know the rate at which this distance is changing, I'm going to take the derivative of this at pi over 3. So I'm going to do, oh, I hope that's, my computer shut off for a second there. I hope it's okay. All right. Anyway, I'm going to do the distance, or the rate at which my distance is changing with respect to theta, of the function I just came up with, all right, at theta equals pi over 3. And again, doing the calculator, and you can do it in rectangular form, it's fine, just do theta, or x instead of theta. And whenever I did this, I got, can't read my handwriting, negative 2. Okay, so that is the rate at which the distance is changing is negative 2 at pi over 3. So you can even see right here at pi over 3, it's decreasing as we continue to move on. That's why it's negative. Okay. All right, so that was C. And now D. All right, now D says a particle is moving along the curve r equals 3 minus 2 sine of 2 theta. So we're looking at that funky one again. So that the derivative of theta with respect to time is equal to 3 for all time greater than 0. So that particle's, like, the rate at which it's changing from the rate at which the angle is changing is a rate of 3. Okay, and I want to figure out what the dr over dt value is whenever theta equals pi over 6. Okay, well, that's simple. We got r equals an equation. If I want to know what the dr over dt is at a specific point, all you got to do is take the derivative. dr over dt is the derivative of r. So dr over dt equals, okay, the derivative of this equation, which is going to be derivative 3 goes away, Derivative of negative 2 sine 2 theta is going to be negative 2 cosine of 2 theta times 2. And we're going to do this at the point theta equals pi over 6. That's all at once. And again, this is calc active. Do it in the calculator. I chose to do it by hand for some reason because it works out pretty nice. But it's negative 2 cosine of 2 times pi over 6 times 2, which is equal to negative 2 times, that's cosine of pi over 3, which is 1/2. Oh, and I have missed something. Whenever I take the derivative of theta with respect to time, I have d theta over dt. I apologize, I missed that. So that's just because it's implicit differentiation. We're taking the derivative with respect to t. So the derivative of theta becomes d theta over dt. So we know that d theta over dt is equal to 3. So I also need to multiply by 3 right here. Apologize, I missed that. Anyway, that value ends up becoming, let's see here, that's times 2, not negative 2. Negative 6, I believe. Yeah, negative 6. And see, that polar problem wasn't bad, right? It was just kind of incorporating a few things there, but hopefully you tried that on your own first and see if you could get it. But now you have the video. Yay! All right, here's the answers, just to kind of give you a little summary of what they were grading. The integral, which is what we got. Here and here, the limits, 0 to pi over 2, and the answer. Okay. Part B, the expression for x, which we did. The answer, which we did in the calculator. The expression for the distance. So I think some students might have overthought that one. Maybe try to do some crazy distance formula thing, but it's simply just the difference in your radiuses. So you take one function, subtract the other one. Then take the derivative of that at pi over 3 and get the answer. And then lastly, we did the chain rule with respect to time t, which we did. They kind of showed it more so along. They didn't really show the work. They just showed the notation. And then the answer for plugging things in. Okay. All right, and that does it, everybody. That does it for our 2 problems today. We're going to do 2 more tomorrow, so be on the lookout for those. Go ahead and try questions 3 and 4, and then watch the video for it tomorrow. Okay? All right. Good job, guys. See y'all tomorrow.